Up until now, in our thinking of elimination reactions, the exercises have given us the product. So when we were thinking about which beta hydrogen to take off, which beta hydrogen that the base will steal, we always just looked at the product that they gave us. Now, starting with exercise 815, they are not giving us the product. We have to figure out what product we're going to get. And so we have to look at all of the beta hydrogens. So let's redraw this molecule. Excuse me, let's redraw this molecule right here, but with the beta hydrogens drawn in. And I'm going to draw it a little larger just so that it becomes a little clearer what we're dealing with. So we still have those methyl groups to the left. You have a methyl group going up and a Cl. Remember, the carbon that has the leaving group on it is the alpha carbon. Every carbon next door to it is a beta carbon. So we have 3 beta carbons here. Now we need to know which of these has hydrogens, because those hydrogens are vulnerable to the base that we're adding, which we've talked about in a previous video is sodium ethoxide. Okay, well, this carbon at the left does not have any hydrogens on it. 4 bonds are drawn in explicitly, and those are to carbons. So a base cannot steal anything from that carbon, so we can't get a double bond going in that direction. We don't have any beta hydrogens in that direction. Each of the other beta carbons does have beta hydrogens. This one on top has 3. I'm just going to draw one of them so that this picture doesn't look too confusing. And the one at the right has 2. I'm just going to draw one of them again so the picture doesn't look confusing. Okay, now let's imagine that each of these is taken. I mean, here we have a base, sodium ethoxide. Remember, the sodium is a metal, and so it gives its electrons away to whatever it's bonded to. Here it's bonded to that oxygen, so the oxygen steals the electrons, and you end up getting that ionic bond. The ET stands for CH2, CH3, and so this right here is Eth. You have an oxygen, so oxide, ethoxide, and you have a sodium. So altogether, that molecule is called sodium ethoxide, and it's a strong base. Now, the fact that we have a strong base is a strong sign that we're doing an E2 reaction. Okay, so let's imagine sodium ethoxide in each of these 2 scenarios. Let's say that we have sodium ethoxide, and it's really the ethoxide that is acting as the base. They separate once you put them into water. So this sodium ethoxide can attack one hydrogen, or it can attack the other. Let's see what happens in each case. Okay, if this ethoxide attacks the hydrogen on the top, well, then those electrons go toward the leaving group. Right, remember, the leaving group is electronegative, so it pulls electrons away from that alpha carbon and becomes slightly negative itself. That attracts the electrons in this bond, so when the base tugs on that hydrogen, the electrons go toward the positive charge to form a pi bond there, and the bond to the leaving group goes onto the leaving group, those electrons. The leaving group leaves, basically. So the product you'd get in that case, you would still have that 6-membered carbon chain, that cyclohexane ring. You would have 2 methyl groups. This here will now be a double bond. So you'd have that, and then the electrons from that hydrogen. There's a double bond. And you don't have the chlorine there anymore. The chlorine left. So that takes into account all of our arrow pushing patterns. That's what the product you get if the ethoxide attacks that top beta hydrogen. Well, what happens if it attacks the beta hydrogen on the right? If it attacks that beta hydrogen, the beta hydrogen is going to leave. The electrons that were keeping it on the molecule are going to go toward the slightly positive alpha carbon, right? The leaving group is electronegative. It steals the electrons from that alpha carbon, which then becomes slightly positive. So, in that case, the electrons go toward that slightly positive charge, that slightly positive alpha carbon, to form a pi bond, and the leaving group leaves with its electrons. Gets kicked off the molecule. So in that case, we still have that cyclohexane ring. Oops. You still have the 2 methyl groups. You still have the methyl group going up, but now this bond, this one here, is going to have a second bond attached to it. Those orange electrons that were going to the beta hydrogen instead are going to be a double bond, a pi bond, between those two carbons. Okay, so we had two beta hydrogens on the molecule. If the base could steal either one of them, and so you end up getting two products, a product for each beta hydrogen that's different. Okay, but you don't get these in equal amounts. You get more of one than of the other. You always get both of them, so you'll always, if you do an elimination reaction, you'll always want to draw both of your products, or all of your products, based on all of your different beta hydrogens, but you also want to be able to say which one is major and which one is minor. And that depends on their stability, which we've explored in a couple previous videos. The stability has to do with the substitution of the double bond. Notice that this double bond on top, right, you could draw little dots there, coming off of those carbons in the double bond are two carbons. So notice that that double bond is di-substituted. On the other hand, if you go through that same analysis with this other double bond, how many carbons are coming off of those carbons in the double bond? You have 1, 2, 3. So that is tri-substituted. So you end up with two products, but one of them is more stable. The more substituted product is more stable. And if you're not feeling comfortable with that, there are two videos you can go back and watch. The first is the one that we did just before this, comparing the stability of alkenes. And then there's an earlier video in the chapter that talks about classifying double bonds and thinking about how those classifications, in terms of being monosubstituted, disubstituted, trisubstituted, or tetrasubstituted, determines the stability of the molecule. So in one of these, the tri-substituted alkene is more stable. That's what we saw in those previous videos, because through hyperconjugation, the pi electrons are able to leak out into the sp3 orbitals of the neighboring carbons the more neighboring carbons you have. So this tri-substituted product is more stable. And if it's more stable, it'll be your major product. The less substituted product is less stable. And if it's less stable, it won't exist for as long. It'll turn into something else faster, and so it will be your minor product. Now, there are names for each of these. The more stable product, the more substituted product, is called the Zaitsev product. And the less stable product, or the less substituted product, is called the Hofmann product. So we have these two products, the more substituted Zaitsev product and the less substituted Hofmann product. And if all other things being equal, if your base can steal any hydrogen at once, then your major product is the more substituted Zaitsev product, and the minor product is the less substituted Hofmann product. And so those would be your two products for this reaction, and the major and minor amount of each. So that's what they're asking for. Identify the major and minor products for each of the following E2 reactions. Okay, so that's one way of thinking about this. But an interesting complication arises in exercise B. So let's go through the same sort of thinking. We'll redraw this molecule out, maybe a little bigger so that we can follow what's happening a little better. So, in this case, we have, we know that it's an elimination reaction. We have a strong base that we talked about in a previous video, potassium tert-butoxide. And that base is going to take one of the beta hydrogens. Well, we need to know where those beta hydrogens are so that we know what direction to put the double bond in. So the carbon that's bonded to the leaving group, that's the alpha carbon. Every carbon next door to that, right, this is the leaving group, bonded to it, alpha carbon. Every carbon next door to that is a beta carbon. And it's the hydrogens on the beta carbons that are going to be stolen by the base. So this one has a hydrogen, and it really has three, that beta carbon at the top. I'm just going to draw one, because that's the only one that only one of them will be involved in the reaction. I'm trying to make it look visually less complicated. And notice that these other beta hydrogens, or I should say the other beta carbons, are really the same, because there's a plane of symmetry in this molecule. So the beta hydrogen on the right and the beta hydrogen on the left would be the same. If you do the reaction on this side, well, then you just have to take this whole molecule and flip it over like a pancake, and it'll be as if you did the reaction on the other side. So to simplify things visually, I'm only going to do show the possibilities on the one side, because they'll both give you the same product. Okay, so in this scenario, there are only two different beta hydrogens that we have. Okay, let's draw out our base. Potassium tert butoxide. TBU, that's talking about a tert butyl group. So there's our tert butyl group. Then you have the oxygen. Now the oxygen is bonded to potassium, which is a metal. So it steals the electrons from the metal and looks like this. So that's our standard base. Oxygen is a small atom with a full negative charge. It's going to want to rip a hydrogen off of anything it can, and any vulnerable hydrogen it can find. So this is potassium tert butoxide, TBUOK. Okay. Now, the significant thing about potassium tert butoxide is that it's very bulky. This tail bumps into a lot of stuff. It's very crowded there. Now, if potassium tert butoxide tries to take this hydrogen here, as it's jostling around in the solution, it bumps into that hydrogen a lot. That hydrogen is open on all sides, so it bumps into that a lot, and it's able to steal that hydrogen quite a bit. Imagine, though, that the tert butoxide tries to steal. So instead of stealing that hydrogen, imagine it tries to steal the other one. Imagine it tries to make its way toward that other hydrogen. Now remember, each of these, this chlorine is gigantic. It's the size of a methyl group, and then there's a methyl group here. Imagine you're this tert butyl group with this big fat tail, and you're trying to move to get to that hydrogen. Your tail sort of keeps you away. It's so crowded there that sometimes you reach, but it takes a special orientation. Most of the time you just bounce off like a billiard ball because everything is so crowded there. In other words, if you have a bulky base, like potassium tert butoxide, one of the hydrogens is easier to attack than the other, the hydrogen that is less crowded. Okay, so let's consider what happens. It steals that hydrogen, steals the beta hydrogen. The electrons go toward the leaving group to form a pi bond because the alpha carbon is slightly positive, and that kicks the leaving group off. In that case, we would end up with this product here. Now, what if it attacked the other place, the place we said was harder for it to attack? Harder to attack because it's more crowded here. Well, in that case, we would have it attack this beta hydrogen, the electrons go toward the leaving group, and kick the leaving group off. So standard A2 mechanism there. That would give us this product. And here, let me draw this in orange. Okay, so if we look back at these products, these different products, and we try to classify them like we did last time, you can see that the product on the top is only dye substituted. product we get on the bottom, though, is 1, 2, 3 tri-substituted. And so this more substituted product on the bottom is technically more stable, and the di-substituted product on the top is technically less stable. And we saw that there are those special names for those. This more stable product is the Zaitsev product, and the less stable product is the Hofmann product. But, unlike last time, because our base was bulky, it was unable to reach this more crowded hydrogen as often. I mean, the reason why this is stable is because there's lots of stuff around it. But the fact that there's so much stuff around it is what made it hard for this bulky base to reach in the first place. And so the stuff that makes the pi bond stable also makes it hard for the base to steal this beta hydrogen. And because we have a bulky base, and it finds it hard to steal that beta hydrogen, even though that's the more stable product, it's the minor product. It's formed less often because the bulky tail of this tert butoxide prevents the oxygen from getting close to that beta hydrogen. Now, this other beta hydrogen on top was open on every side. It was very easy for that bulky base to reach it. And so even though that forms the less stable product, it ends up being the major product when we use a bulky base. Right. The thing that makes this less stable is that there are fewer carbon branches attached to it, but that is also what makes it easier for the bulky base to get close to it. So the result that we get is the opposite of the result that we saw originally. In the last example, this base that we used was not very bulky. It was a skinny base. It could reach either of the hydrogens equally well, and so it formed the more stable one, the Zaitsev product, more often. That was your major product. But when we use a bulky base, it has a hard time reaching the hydrogen that gives the more stable Zaitsev product. So the Zaitsev product becomes the minor product, and the Hofmann product, which was less stable, but which the base can reach all the time, becomes the major product. So let's make a tiny table to sort of summarize our thinking on this. We can have two types of bases. We could have skinny bases, like we saw at first, or we could have bulky bases. Now, examples of skinny bases and bulky bases. A skinny base is one that's small, so you have that oxygen with a full negative charge that's going to attack the first thing it comes across, but it has something small attached to it, like a hydrogen, or a methyl group, or an ethyl group. Those are all small, skinny branches that can wiggle their way into close to any beta hydrogen. And these are often paired with a cation, usually it's sodium, to help stabilize those charges. So you can see these as NaOH, NaOMe, or NaOET. So sodium hydroxide, sodium methoxide, or sodium ethoxide. All bases that we saw when we were drawing the mechanisms for these reactions earlier. So I'm just going to draw that clean version of this, the clean version of those bases here. So sodium hydroxide is a skinny base, sodium methoxide is a skinny base, and sodium ethoxide is a skinny base. On the other hand, we saw that potassium tert butoxide was a bulky base. that tert-butyl tail, it makes it very bulky. And the way you'd see that written is T for tert, Bu for butyl, O for the oxygen, and then K. So TBUOK, and often this B is capitalized. Okay, so that's how you can recognize skinny bases and bulky bases, and let's now summarize what we learned about their behavior. In the case of a skinny base, they can reach any of the beta hydrogens. So the Zaitsev product, the more substituted product, is the major product. And the Hofmann product, the less substituted product, was the minor product. The case was exactly reversed in the case of bulky bases. For this one, in bulky bases, the Zaitsev product was the minor product. It was harder for that bulky base to reach that more substituted position. And the Hofmann product, where there are fewer branches coming off of the double bond, that's the major product because it was easier for that bulky base to reach the beta hydrogen in that case. So we're going to use this table now to more quickly explore these next exercises. Okay, so we'll use this table. Let me just have that there. All right. So we'll go through our similar analysis like we were doing before. In the future, we won't draw the whole mechanism out, but since we're still learning and practicing, I'm going to draw the mechanisms out here so that you can see them. So we have our methyl groups and our iodine. So that's our substrate. Remember, the alpha carbon is the carbon that has the leaving group attached. And each of the carbons next door are beta carbons. If those beta carbons have a hydrogen, those hydrogens are vulnerable to attack from the base. Now here, our base is sodium hydroxide, and really it's the OH. Sodium is a metal, so it gives its electrons away to whatever it's bonded to. Here, that's the oxygen, and so that's going to have a full negative charge. So that OH is going to act as our base. Now, it can steal a few different hydrogens. It can steal a beta hydrogen in that methyl group. Notice this is another methyl group, just like the one above, and so that would really give us the same product as above. They would both have a double bond going toward a methyl group with a double bond next door. So to make it visually simpler, I'm only going to consider one. And then we could have another hydrogen at this more substituted position, this different position to the right. So those are the two options. Imagine that our skinny base, or I should say, imagine that our base, sodium hydroxide, which is really the hydroxide, swoops in. It can attack in two different places. It could attack the beta hydrogen on top. Remember, this leaving group is electronegative, so it pulls electrons to itself, and that leaves the carbon that it's bonded to, the alpha carbon, slightly positive. So when the base tugs on the beta hydrogen, those electrons go to form a pi bond toward that positive charge, and they kick the leaving group off. So when the dust settles, what you would be left with in that scenario is two bonds, your pi bond going to that methyl group. Notice it's going toward the beta hydrogen that you stole the hydrogen from, toward the beta carbon that you stole the hydrogen from. The hydroxide can also steal the other beta hydrogen. And for a similar reason, those electrons can go toward the slightly positive alpha carbon to form a pi bond there and kick the leaving group off. In that scenario, you would have just a single bond there. You'd have a pi bond going toward the hydrogen that you plucked off. So these are our two products. Okay, well, which one is major and which one is minor? Well, first we have to know which one is the Hofmann product and which one is the Zaitsev product. So let's figure out how substituted these are. This carbon is bonded to 2 other carbons. or the two carbons in that double bond, are just bonded together, are just bonded to two other carbons. So that is going to be di-substituted. If we think about the carbon at the bottom, or the double bond at the bottom, those carbons in that double bond are bonded to 1, 2, 3 other carbons. So that is tri-substituted. The tri-substituted product is the more stable product, and that's referred to as the Zaitsev product. The less substituted product is the less stable product, and that is referred to as the Hofmann product. Okay, so now we need to know which one is major and which one is minor. For that, we have to figure out what type of a base we have. We have sodium hydroxide, and sodium hydroxide is a skinny base. That means that the Zaitsev product is major and the Hofmann product is minor. The Zaitsev product is our major product because this skinny base is able to reach every beta hydrogen. And so it'll create the product that's more stable more often. It'll still create the minor product, the Hofmann product, the less stable product, but that one will break down because it's a less stable molecule, and so you'll have a relatively smaller proportion of it. And so those are the two products, major and minor, for this reaction. Okay. Just to avoid making these videos excessively long, I'm going to cut this one off here. We'll continue with D, and then we'll do E and F in a separate video.